So nonlinear modeling. So today we will talk a little bit about nonlinear modeling. As you know, you should know a little bit about nonlinear modeling because performance-based design is used many places. So you should have some idea about that. So this is an overview, what behavior to capture, what level of accuracy needed, and what are the computational trade-offs. So it's a little bit light here. So the behavior, important thing is, what do you want to capture in nonlinearity? How far are you going to go in nonlinear capture? And I will show you after this one. Level of accuracy is very important. There's a difference between being accurate and being precision of the numbers, right? Two different things. So for example, you might get numbers which are highly precise, 10 raised to power -5 accuracy or 7 decimal after the point. But that is not the one that we are looking for. We're looking for correctness of the results. That means whether those numbers are correct or not. So accuracy in terms of the numbers, digits is not important. The significance is the order of the number, especially for nonlinear analysis. In nonlinear analysis, there's no such thing as accuracy because this is all assumed in many ways. So you will, and it's all based on how you assume nonlinear properties. So numbers have no accuracy issue. It's the correctness that you're looking for. Are they correct? Reasonably correct. And so you should focus on that. So normally we have some idea of the ratios with the linear analysis. That's how we know it's correct or not correct. It should not be. So in general, nonlinear analysis, especially if you put all the nonlinearities for earthquake, the base shear, for example, should not be more than elastic. That's check number one. Even if it is whatever it is, it cannot be more than elastic. It has to be less than that, generally. If it is more than that, you have to figure out or find why. What is making it more? Generally, it should not be. Things like that, you have to know. So sources of nonlinearity. Nonlinearity can enter at every level of the structure. We have already seen that. So we have this diagram we have seen before. So nonlinearity, the material level, stress strain curve, we talked about last course. Section nonlinearity, moment curvature, member nonlinearity, moment rotation, and structure nonlinearity, P delta, P delta, and also the force and drift. So all of this nonlinearity you need to capture step by step, starting with the material all the way to the structure. So we talked about this one, FD curve. So you need to capture now the first yield, hardening, ultimate, ductility limit, residual stress, and also the damage. So we have studied a little bit about all of that, but just now summarizing everything. These are the damage models that you have to choose for nonlinear analysis, hysteresis model. Depending upon the type of material, depending upon the type of elements that you're using, you will have different damage models. So this is the typical flag model. This is the theoretical, cyclic. This is with more damage. This is for concrete, and so on and so forth. So you need to understand a little bit about what kind of damage model is relevant to your structure. Normally, we use Takeda model for concrete, reinforced concrete. But that may be useful for the BRB and so on. So it depends upon the element that you're using. So those are the actual ones. And normally we convert that into a backbone curve, simplified backbone curve with one of those models attached. So this is the AICE's typical, you will find this data everywhere. So you have this 4 or 5 points, you have these values and numbers and ratios, and then we have the acceptance criteria. So this is both the input and the output. That's the interesting part about this. So this is both the input and also the output. So when you define the material, when you define the moment rotation curve, moment curvature curve, you input curve like this, and on that, you specify those performance points. So the output curve will be similar. And then depending upon where it has reached, then you can check whether, because input is based on material and section, output is based on structure response. But the plot is the same. The limits are the same. So that's why it's easy to check the two things together. So normally we try to keep the structures before this point. And we try to keep the structure here for service level. We try to keep the structures here for code-based design, and then collapse prevention up to here. And this one is that it is already collapsed, but still it has a residual stress. So we, depending upon the level of earthquake and so on, we can choose from this severity. So materials, you already know material, section, member, structure. We have studied most of these things already. So nonlinearity, so material nonlinearity, elastic assumption misses all of this. That's the important thing that we can remember, that nonlinearity is missed, geometric nonlinearity is missed, contact and separation, like I mentioned to you, that is missed, and then friction and sliding is missed, and hysteresis damping is missed, and cumulative damage is missed. All these things you cannot capture in a linear elastic analysis. So if we are interested, which we are for performance-based design, that we need to run the nonlinear analysis, and we need to be aware of all of that. So 4 sources of nonlinearity: material, section, geometry, and boundary. So you know where it is coming from. Now, nonlinearity is present in everywhere, but the sources are very clear. First of all, it's material. And we already know stress strain curve can capture that. Section is captured by cracking. So cracking of the section is in section. Geometry, P delta effects, and then boundary, that means solid structure interaction, or sliding, or contact lift off, or separation, or all of those things will happen in boundary. So you need to step by step capture these sources of nonlinearity. So we use gaps and friction over there. We use P delta over there, moment curvature over there, stress strain over there. So this picture gives you the whole entire spectrum of material, behavior, and modeling. This is what we are trying to capture. This is the way to do that. So with stress strain curve, fiber models, and layered shells can capture that. Physical behavior, moment curvature response, hinges, and fiber sections. Geometry, P delta, small p delta, member buckling, analysis settings, and geometric stiffness. Boundary, link elements, nonlinear springs, and so on. So we covered everything on this one. So nonlinear links are especially useful when you do the nonlinear modeling, and especially in the last portion. The lift off of the wall, for example. So nonlinear modeling you can do 3 ways: lump plasticity, fiber modeling, and distributed plasticity. And ETABS or SAP have all 3 options, modeling that you can handle. So lump plasticity is that we put the nonlinearity in one location, one point. So concentrated plasticity, plastic hinge concept, localized inelastic action, member level input, and so on. And then fiber modeling will give you the section level. So it's the next level. So the first one is just in the member directly, put everything together. Section model is that you do the distribution of the material inside. So fiber modeling will give you material level definition, stress strain curves, distribution of nonlinearity, reinforcement, and all. And then from there, the capacity can be calculated. And then distributed plastic inelastic actions over the length. That means you model the entire member to be nonlinear, not just one section. Normally in section, we just take one section. But if you, for example, you have a shell slab, we can put the nonlinearity in the entire slab, not just one location, everywhere. Similarly, for the wall, you can put the nonlinearity in the shell elements which are forming the wall in every direction, not just in one bending direction. So this is the plastic hinge, fiber hinge, and finite element. So that's how the 3 are different. The first one is that you put the fiber hinge at this location with a certain, first of all, just a point. Second one, length, over which it will yield. The fiber section, put many sections and different materials, and then program calculates as is needed. And here, shell elements, and then take every element and put the nonlinearity in every element, in every direction. So that's the most complete nonlinearity that we can do. And this is quite recent in ETABS. And when in SAP, when it came in the program, we did a lot of theses to apply that to verify the lab testing. So for example, you put a wall in the test and you test it, and then you create a shell element, nonlinear shell element, and you try to compare the results. So before we start using it, we did a lot of testing in the lab to make sure that we understand how this modeling is done. So lump nonlinearity, we can put the hinges, beam, column ends at free supports, points of maximum bending moment, midspan, and so on. So you can put the hinges here, and we can capture. So this is very important. What kind of nonlinearity can we capture, or what kind of nonlinearity we can specify? Moment versus rotation, just M3, 1M and corresponding rotation. Shear force versus shear deformation can also be nonlinear. So you can specify nonlinear shear spring. Axial force versus displacement, axial force versus axial, torsion versus twist. So these are the types of nonlinearities that you can provide hinges in the beam or in the column. So plastic hinge, basic nonlinear modeling. So we have plastic hinges, axial, shear, torsion, flexural, and then coupled. Everything is combined. And then we have moment rotation and moment curvature inside in fiber hinge. So when you drop down ETABS for hinge, you will find about 11, 12, 15 types of hinges that you can choose. And then you can specify the data for each one of them. So you can, if you drop down, there are so many types. So each one of them has its own form. So it's like hundreds of forms inside the program to specify the data. So these are uncoupled, one hinge, one direction at a time. These are coupled interaction hinges. So as you go to interaction hinges, they become more complicated. But true shear moment interaction doesn't exist in any of the SAP or ETABS models. So shear moment interaction is not included. So these are the concentrated fiber and plastic hinges. And obviously, we already talked about the use of the nonlinear links. So now coming back to that point. So now this is the difference between the two approaches. One is that you put the lump plastic hinge between the column and the beam. That means you embed the nonlinearity as one point inside the beam and assign the nonlinearity there. So this can do many things. But it cannot do separation. It cannot do all sliding and friction and everything that we talked about. So second option is that you separate the beam and the column and put in between this link. Now you can handle every possible complex behavior that you want, even sliding of the beam, separation of the beam, moving away, hitting the beam, something. So now you can handle all of that. So that's where the power of the nonlinear links comes in, that you can put nonlinearity two ways. One is that you put a hinge, assume that it will deform there. Second is that no, break it up and then link it one step at a time, 1 degree of freedom at a time, one behavior at a time. So some can be linear, some can be nonlinear, some can be free. So you can create very complicated connections by using nonlinear links by first separating elements and then reconnecting. So this is multiple links. This is one link with multiple degrees of freedom, two separate approaches. Like I said, one link with 6 degrees of freedom, then multiple links, each with different behavior. So this is the nonlinear link properties, some forms from there. A lot of data is needed once you do that. For nonlinear, first start with simple, linear plus P delta, default settings, and pushover. So when you start doing nonlinear, just don't rush to the most nonlinear problem because you will not understand what happened and you don't know whether it's correct or not. So normally when we start, we have the linear analysis as a basic reference because that is what you understand. Next one is a little bit nonlinearity, P delta. Then you see what is the effect of the P delta. Then you go, okay, pushover plus P delta. Then this one, then this one, then this one. Then you have all the results to compare. So you know that nothing will go completely out of hand. So you can then trust them one by comparison with other methods. So that's the way that you keep a control on the final output. So simple, linear plus P delta, default hinges and pushover, minimal, intermediate pushover, user-defined hinges. You actually give data for every hinge, and then nonlinear responsive tree analysis with explicit elements. Most difficult, most advanced. You have to have all the data and a lot of input. But this is a good way to go there gradually and save all the results with you. So you can compare at all times that you're going in the right direction. So this was a small building that we tried to model this one, just an example. So we can put the beams, it's a school building, small school building. We use it for various tests. So you can add the hinges to this one for different purposes. For example, this is the building here and foundations, frames, beams, and all. And then you can put the modeling of the beams. So you can put the hinges in the beams like this one to capture the nonlinearity. Let's say you want to do seismic evaluation, then you will put the hinges like that. So then you can put the plastic hinges in that locations. And then this was the way to do that. You put the hinge there, and from there you define the cross section. Then moment curvature curve for that will give you that this is the real moment curvature curve. This is the idealized moment curvature curve. And then you put that back into the hinge and then add the plasticity model onto that one, the damage model onto that, and then you have the analysis from there. So that's the way that you can just put a simple hinge there and do the analysis. So more details about that and how to define that, more details about that. Shahzad to make these videos at that time. So assign those hinges there. So similarly for columns, you select those locations, normally top and bottom, and then you add columns. And then you use the PM interaction concept, and then you choose the PM hinge from there, PMM hinge. And then fiber section also can be used. Normally we use fiber section for columns. And the reason is, in the beam, we are using moment hinge. And in column, we are saying that we don't want to use PMM hinge, which is this option, first one, PMM hinge. Why we don't want to use PMM hinge? And why do we want to use fiber hinge? The question is, for columns, for beams, we decided to use a moment hinge. But for columns, we normally say that we should not use the plasticity, the fixed plasticity hinge. We should not use the PMM hinge. We should use a fiber hinge. Why? What's the difference? And why do we say that? So we cannot specify one single hinge there, one single curve. We will have to specify a very large family of moment curvature curve. Not only that, but direction also. Because in each direction, moment curvature curve is different. And at each load, it is different. So you will have to input like 100 PMM curves to capture all the behavior for actual loading condition, which is not practical. Although you can do that in SAP, we have the option, but it's not practical. So that's why we put the fiber hinge. We tell the program the details of the column, where is the rebar, where is the material. We define the section, and then it generates the PMM hinge as required for a particular load combination at that time. So it's a live development of the hinge and use that one. So that's why it's not practical to use the simple hinges. We need fiber. So that's the reason. So because we have all these interactions going on here. So it's much better to use the fiber hinge. You specify the section, actual section over there. And from there, like this one, so the program will generate the hinge properties at that location when it needs it for the axial load for the moment direction. That's the difference. So that's the way to define this one, assigning PMM PMM hinge on fiber hinge. So once again, same way, go there, select that one. So similarly, we do the fiber one. For shear wall modeling, we have two options. So one option is, so modeling layered shell fiber approach, wide column, just like a column, we use like a column, and then nonlinear shell plus shear springs. And we can use any of these. Normally for shear walls, people still prefer the fiber hinge just like a column. So they think about the shear wall as if it is a big column section. As I mentioned to you, CSI call we still use for shear wall also. So people, many programs, by default, people who are not familiar with nonlinear shell, layered shell, they will still use the fiber hinge modeling for the shear wall as well. Define the cross section, and then program calculates the PMM for that and assigns it over there. Or they can use what is called the multi-link vertical elements. So it's like a fiber hinge, but it is not combined back into the section. It is kept as a cross section with the physical dimensions, assuming that they are all moving together, deforming together. So that was developed many years ago, and people still use that. So in case of the fiber model, you specify the fibers. So this whole section will be one fiber, one fiber, one fiber. So few fibers are defectified concrete and steel, and then based on that, the corresponding materials are assigned, and then you get the curve. So it's just very rough meshing is done so that you can quickly generate the required behavior. So each line, each fiber is vertically connected, and they deform together as a big cross section. So they are not brought back into single cross section with one line. So the wall geometry is still maintained. So wall is actually divided vertically into these line elements that deform together with a shear fixed. So that's the fiber section. And then finally, the layered shell. So layered shell is the most complex modeling that you can ever do at the moment in SAP, any tabs. So basically, if this is the section of the wall, and we have vertical reinforcement, okay, and then you have horizontal reinforcement, let's say here, inside or outside, doesn't matter, depending upon where you see it. So which means that now this wall section has one layer here, which is the cover, one layer, which is this bars, one layer, which is this bar, this concrete, this bar, these bars, and this one. So there are 7 layers in this section now. So you can create a shell section with 7 layers, and each layer has its own property, vertical, horizontal, shear, whatever. You can also put the reinforcement on angles. So you can specify the angle, and then you can assign the stress strain curve to each layer. So this is very, very detailed cross-section modeling where each layer has its own nonlinear properties. So you can model very complex behavior both for slabs and for walls. And this behavior, what is called isotropic and orthotropic behavior, can also be modeled. So this can also be used for one-way behavior, deep beams, many applications. So it's a very powerful element that you can use to do full nonlinearity, which is distributed. So it's no longer section-wise, but it's everywhere. And then P delta, very important to set this one here. So like I said, large displacement. So P delta, large displacement, means that the P delta combination and magnification of forces due to deformation and large displacement mean the geometry is no longer original. So the deformed geometry is actually used. For example, the biggest example for them that will be that, let's say you have a beam. Yeah, now snap through. Okay. It will be something like this. Okay. Can you push this in the center? This is called snap through. That here it is an arch, right? This one, if I deform it enough, it will become flat like a beam. And then if I deform it more, it will become like a cable. So that means the stiffness will change drastically from being an arch, which has a lot of stiffness as an arch. But if the deformation becomes very large, it will become flat. Beam as this very thin as a beam, it will have no stiffness. And then if I bend more, it will become like a cable. It will again have stiffness. So this is called a snap-through problem in nonlinearity. He's searching what does that mean, snap-through. So this is the line. So you have, let's say to make it interesting, I put a hinge here and supports here. So now if I apply the load here, this will act. So if this is the P and this is the delta. So what will happen is that now P is applied here. So it has a lot of stiffness because this is a truss, right? This is a support here. This line does not exist. Okay. So then that means the stiffness is very high. So if deflection and stiffness will go like something like this, right? And then after the deflection is increasing, it will become a flat beam with a hinge. Of course, flat beam with a hinge has no stiffness, right? Because it's a hinge. So it will suddenly drop to zero stiffness. And then again from here, in the other direction, it will become load and can still carry the load in tension. Here it is carried the load in compression, and now it is carrying the load in tension. So that means the stiffness will increase again. So this is called a snap-through problem. That structure has a lot of stiffness, and then suddenly no stiffness, and again a lot of stiffness. So then drop here, and suddenly negative stiffness with negative deflection, negative load, you can say. So this will be a snap-through problem now. Go back again. So this kind of behavior is only possible when you use large displacement. You are monitoring the change of the structure also. But in a small displacement example, it will always remain an arch, never become a beam or a cable. So if the structure is going to deform so much that its geometry will change significantly, then we activate the large displacement option in the program. So that's and then P delta only, P delta plus large displacement, nonlinear geometry, and so on. So it's so many things to do with P delta settings. Then last is running and interpreting the results. So in this one, nonlinear static pushover, as I mentioned to you, you must run normally to get the understanding of the behavior. And then nonlinear dynamic time history analysis to capture the actual response, or so-called actual response. So from there, we start with the gravity. Yeah, this is one mistake that most people make while running nonlinear analysis. Nonlinear analysis must start after the gravity analysis is complete and the load has been stabilized. So you first apply the gravity load, let the structure deform, and start from there the next nonlinearity. Because people forget to apply the gravity load and just start with the later load nonlinear analysis, which will never work. So make sure that you start with gravity, lock that deformation and forces, then apply the pushover. So then displacement control and everything. So pushover, nonlinear time history, ground motion, integration method, time step selection, damping matter, so many things to do here. Of course, I mean, I cannot cover everything, but I'm just giving you an overall view of what is involved in a nonlinear analysis and nonlinear modeling. Convergence is one of the biggest problems in nonlinear because nonlinear is iterative. If you remember, I told you we are looking for a solution that we don't know. So a program is trying to find it step by step. So it may never find it, or it may go in the wrong way. So convergence is one of the problem in nonlinear analysis that we have to set properly, or we have to play with convergence tolerances and all of that stuff. So these are the solutions to that. Results, always we look for these things, yielding immediate occupancy, life safety, collapse prevention, ultimate loads, and failure. So depending upon what you're doing, you should be looking at these results at all times. Okay, so let's stop here. That's the end of part 5 on modeling techniques.